Good evening, everyone. Hope you're all doing well. We'll get started with continuing on where we left off with nomenclature and naming. So this whole chapter has been on naming compounds. Up until this point, we've only done ionic stuff. So that means a metal with a non-metal. That metal can have a predictable charge or it can have an unpredictable charge. If it has an unpredictable charge, we need to give a little bit more. We need that Roman numeral. It can also contain a polyatomic ion. So I'm going to give you guys a couple formulas to give me the name and then name to give me the formula. And I'm going to jumble them together. So I'm going to mix together type 1 and type 2 are predictable and unpredictable charges. And I might throw in some polyatomic ions in there as well. If you don't have a formula sheet and you don't have some sort of polyatomic ion reference, get that ready. All right, so let's do C little o big O2. K2SO4. ZN3PO42. FeOH3 Li2O. Okay, so you're going to give me the correct name for each of these things. And then over here, I'm going to write a couple names and I want you to then give me the correct formula. So titanium 3 sulfide. Sodium carbonate. Nickel 1 acetate. Silver nitride. For fun, we'll do silver nitrate. So for each one, you might want to classify, is it a type 1 with a predictable charge? Is it a type 2 with an unpredictable charge? And you might want to identify and or put a note if there are polyatomic ions in there. I'll give you all a couple minutes for that. Say I'll give you 6 minutes for it. Okay, so let's come back together. We'll go over these. So I'm gonna make a little note just on the side, like important things for each compound. So this first one is ionic, and it is also, it's type 2, meaning it has an unpredictable charge. So when we have that unpredictable charge, we know we're gonna need a Roman numeral. So cobalt combined with oxygen is going to be some sort of cobalt, parentheses, oxide. Right, to figure out the charge on this cobalt, we need to go from what we do know, which is we do know the charge on oxygen, to get what we don't know. Oxygen always has a 2- charge because of the column it's in, and there are 2 of them. So there's an overall 4- charge happening on the negative side of this formula unit. So the positive side has to be equal and opposite to that because we have a neutral charge for every one of these. So this will be a 4+, or IV. This next one here, this is ionic. It's type 1 instead of type 2. So potassium has a predictable charge. So we don't need a Roman numeral because potassium will always have a 1+ charge. The other interesting thing it has, though, is that it's got a polyatomic. So that SO4 thing is sulfate. If you ever get to a place where you're naming and you're like, oh, this isn't following the rules, like there's too many different types of atoms, it's a polyatomic ion. So potassium and this thing is called sulfate. When we name that, we just go potassium, sulfate. We don't change anything about the polyatomic ion. We just keep it as its true name. Where do you find those polyatomic ions? They are on a polyatomic ion list, in the appendix in your text, or you can find one online as well. This next one here is very similar. I don't know why I didn't put parentheses around there. I've had a long day. I've taught nomenclature 3 times outside of this today. Okay, so we've got zinc and we've got phosphate. This is ionic. It is type 1, even though zinc is in the middle with the transition metals. Remember that silver, zinc, and aluminum we treat as a predictable charge. Okay, so we don't need a Roman numeral for zinc because zinc is always 2+. So if you don't have that on your periodic chart, put in the box for zinc that it has a 2+ charge, and that's it. And same thing for silver, it has a 1+ charge. There's also a polyatomic ion in here. Sorry that I didn't put the parentheses. It looked like there were 42 oxygen. There are not 42 oxygen. It's PO4 and we have 2 of them. So this thing becomes zinc, and then this packet over here is phosphate. We just list the polyatomic ion again. We don't IDE it or anything like that. This down here, this is ionic. It's type 2 because iron has an unpredictable charge. So I know I'll need a Roman numeral. And there's also a polyatomic in it, hydroxide. So I know that this is going to be iron with some sort of Roman numeral. And that polyatomic ion there is hydroxide. So even if it's a polyatomic ion instead of a nonmetal, you still treat it the same way. Hydroxide, OH, always has a -1 charge. That is what is part of the definition of hydroxide. So -1. And how many are there? There's 3 of them. So we're going to multiply that by 3 to get an overall -3 or 3- charge. If that's a -3 or 3-, that means our iron has to be 3+ to balance out 3 of the hydroxides. We're done. This guy here, ionic, and it's type 1. Lithium has a predictable charge, so I don't need a Roman numeral. All I have to do for this one is just call it lithium oxide. Any questions on those, or going from formula to name? Any confusion on where any of this stuff came from, where any of these numbers came from? You can throw it in the chat. Okay, the lab for this week it gives you a lot of practice on these. On the lab, the very first page of the lab, and talk to Cynthia about this, There's a section at the top that talks about like Lewis dot structures and stuff. Just skip over that because we're going to go over Lewis dot structure next chapter, and it's just not worth it to teach it to you right now. So you can ditch the very top of the first page of lab 7. We're doing lab 7, which is the nomenclature lab. But I do want you to do the 2 matrices box underneath it. So there's a series of like graph boxes where you have a metal and a non-metal and you're combining them in different ways. That I do want you to do, but the first third you can ditch. The other 2 pages of the lab, one page will be all formulas going into names, and the other page will be a list of names going into formulas. It's a bunch of practice. They're all mixed together. Okay. So let's see. So going the other direction, usually people have like a way they prefer. They find either this way easier or they find this way easier. This thing here, titanium 3 sulfide, this is ionic. It's type 2 because it has a Roman numeral. And sulfide is talking about the element. So we don't have any sort of polyatomic ion here. So when we have anything ionic, we need to balance charges. So I'm going to first write out my metal with its charge. Now this here is telling me the charge of titanium. It's not telling me the number of titaniums. A lot of times people see that 3 and they want to drop that down as its subscript. Don't get ahead of yourself. This is telling us the charge, which is 3+. Sulfide is talking about sulfur, and sulfur is always 2-. Flip flop, and I need to have 2 titaniums for every 3 sulfurs, right? Remember the 3 drops down there, the 2 drops down there. That would give me an overall 6+ charge on the metal side and a 6- charge on the non-metal side. So the whole thing is neutral, because with ionic compounds, the goal is to get this neutral charge. Sodium carbonate, this is ionic. It's type 1, it's predictable. So you'd get it off the periodic chart, and there is a polyatomic ion in this. How do I know it's a polyatomic ion? Because ATE is a good indicator that you need a polyatomic ion. Carbonate with sodium. All right, sodium Na, it's in column 1, so it always has a +1 charge. Carbonate is CO3 with an overall 2- charge. It might serve you to circle the atoms of your polyatomic ion and keep the charge on the outside. So you know that whatever we do to carbonate, we have to do the entire thing. In this case, it's not a big deal, but let's see, we've got a 2 here. So that's going to be dropped down to the sodium, and we have a 1 here, which is dropped down to the carbonate. So I need 2 sodiums for every 1 carbonate. If you only have one of the polyatomic ions, you just write it out. You don't put parentheses. Okay, parentheses are only used if you have like 1 or more, or I mean, if you have 2 or more. So if we had like happened to have had 2 carbonates or 3 carbonates, then we're going to go ahead and put in parentheses, like you would see over here. You see phosphate, and there's 2 there. Okay, the next one here, this is ionic. It's type 2, and it also has a polyatomic in it, acetate. ATE, again, good indicator, it's a polyatomic ion. So I'm going to write the metal with its charge, nickel. And if you go to the periodic chart and you're like, what is the charge on nickel? I can't find it. You're not going to know it because of its location on the periodic chart. You're going to know it because it's written here. So nickel has a +1 charge. Acetate is going to be C2H3O2. And this whole thing has an overall -1 charge. Okay. This is a 1-to-1 ratio. So we just write this as NiC2H3O2. Again, we don't need parentheses around it. Someone who's familiar with chemistry would be able to see this and say, hey, this is nickel 1 acetate. You don't have to like define the polyatomic ion with the parenthesis. This next one here, silver acetate. So silver, although it's sitting in the transition metals, we treat it as a type 1 because it has a predictable charge. So iron, ionic, type 1. Nitride, IDE is talking about the element, nitrogen, right? We eyed the elements. So I'm going to take silver, Ag, which always has a +1 charge. How do you know that? Because you've written it in the box with your little silver to say that it has a +1. Nitride is nitrogen, so that's N with a 3- charge because of its location in the periodic chart. We flip-flop, and we're going to need 3 silvers to balance out every one of those nitrogens. So Ag3, N1. This one looks very similar, like the wording is almost the same except for 2 of the letters. But "ide" and "ate" mean different things. So this is ionic, it's type 1, and nitrate is a polyatomic ion. So we write our metal out, Ag with a plus, nitrate, NO3, and this thing has a minus charge. And again, if you want to sort of circle that or group it together, know that you need to write that thing down. Flip flop, and it becomes a 1-to-1, or we get Ag, NO3. Somebody said for the multiple of carbonate, I'm a little confused. There are 3 in the packet, but it doesn't get parentheses like the 4 packet for the zinc. Yeah, so we don't put a parenthesis around it. It's just inferred that if you have one of them, you assume it's a packet, right? If I had more than one of those, then I would write the packet, or I would put the parentheses in. Is that clear? No. Okay, let's do it. I'll show you 2 examples. You can be honest with me. It's okay. So let's do magnesium nitride, magnesium nitrate, and magnesium nitrite. Oh, and we're going to do one more. We're going to do potassium nitrate. Okay, so I'm going to give you like 2 minutes or so to write the formulas for these guys. Magnesium nitride ending in IDE. Magnesium nitrate ending in ATE. Magnesium nitrite ending in ITE, and potassium nitrate ending in ATE. And Betsy, yes, if there's more than one packet of them, then you use parentheses and put the number of them on the outside. Hopefully when we go over these, it'll clear that up. Okay, so this first one is ionic. It's type 1. Nitride is talking about nitrogen, so no polyatomic ion here. Magnesium is Mg with a 2+. Nitride is nitrogen and with a 3-. So we're going to flip flop. We should get Mg 3N2. These are the polyatomic ones. Where do you get the Roman numeral? We won't have any Roman numeral for magnesium because magnesium always has a 2+ charge. Why? Because it's a main group element. It's in column 2. It always has a 2+ charge. So I would never call this thing magnesium 2 nitride. This and this are redundant information. That would be an incorrect name. Magnesium nitrate is magnesium, which is Mg with a 2+ charge, and nitrate is a polyatomic ion, which is NO3 with a - charge. When I flip flop, I'm going to circle this. Okay, whatever I have here, I need to put on the outside of a parentheses, and then this one gets dropped to the magnesium. So we have one magnesium. We're going to have multiples of the nitrate, so I'm going to put it in parentheses and then take that 2 and wrap it around the outside of the parentheses to let me know I have 2 of those packets. Magnesium nitrite sounds so similar, right? But it's a different thing. This is Mg. This is ionic. It's type 1 and it has a poly. Sorry, ionic. This is also type 1 and it has a poly. Magnesium is a 2+. Nitrite, NO2 with a - charge. Remember, your ites are always going to be 1 oxygen less than whatever your 8 is. So if you know your 8s, you can figure out the ite just by stripping a single oxygen away. Flip flop, and if you want, you can circle this with the charge on the outside. I know that I'm going to need 2 of these packets to balance out every 1 magnesium. So Mg parentheses NO3 end the parenthesis and then wrap that 2 around the outside. Now the reason I threw this one in here, potassium nitrate, is because in this case, we won't need parentheses with our polyatomic ion. This is also ionic type 1 with a poly. Potassium K+, nitrate is NO3 with a - charge. I'm gonna circle that thing. This says, hey, give me 1 of these for every 1 of these. So KNO3 would be the correct way to write this. We would not write it as K parenthesis NO3, okay? No need for the parentheses. Is that making more sense with the parentheses, the use of them and not? Really only want to use the parentheses in situations like here or here, where we have multiples of the polyatomic. We just have a single polyatomic, just write it out, smushed up against the metal. Any other questions? All right, so you at this point can name, or you have the system at least, to name any ionic, which is a metal and a non-metal. Sometimes you'll hear the word ionic loosely called a salt. A salt just being a metal combined with some sort of non-metal. So what happens if we are in a situation where we're molecular? So like this here, CO2. If we want to name this, which this is carbon dioxide, what is our system? It's totally different than a metal and a non-metal. So you do need to first identify that it is a molecular compound. And the way you do that is you just know that it's 2 metals smushed together. Real quick, yeah, this slide, I'll show you this real quick. We kind of already talked about it before we get into the other things. So naming polyatomic ions, or sometimes the ones that contain oxygen are called oxyanions. Just know that your ite is 1 oxygen less than your 8. So nitrate is NO3-, so nitrite would be NO2-. It's not the number of oxygens you have that's 8 or ite, it's just their relationship to each other. So ites always have 1 oxygen less than 8. If you look over here, sulfate is SO4 with a 2- charge. Sulfite would be SO3 with a 2- charge. Phosphate, phosphate is PO4 with a 3- charge. So phosphite would be PO3 with a 3- charge. You strip an oxygen away, you keep the charge the same and just strip the oxygen away. There is a continuation to that series. I'm not going to test you guys on hypo or PERS, but like if we were to look, for instance, at chlorate, chlorate is ClO3-. Chlorite would be 1 less oxygen. Hypochlorite would be an oxygen even farther less than that. So 3 to 2 to 1. Hypo being under, less than, so hypoglycemic. If we wanted to increase our oxygen, if we were at the chlorate, and we wanted to have 4 oxygens, we would put the word per in front of it and we'd have perchlorate. So this is a series. Perchlorate has the most oxygens, then it drops 1 oxygen to chlorate, then 1 to chlorite, and then to hypochlorite. You can see the same thing happening here with the bromate series. We have perbromate has the most oxygens, 4, bromate without the per has 3, bromite has the 2, and then hypobromite has 1. Okay, so back to naming molecular compounds. That first part of the class, I feel like, or this chapter takes up like 90% of it. The molecular compounds are pretty easy to name. So once you've decided it's 2 nonmetals, it's molecular, they're sharing their electrons and they're forming molecules. This is how you're going to name them. You're going to take the name of the first element that's listed, which is usually the more metal-like thing. And you're going to put a prefix in front of it that tells you how many of those you have. The whole idea of flip-flopping charges and making something charge neutral, just get rid of all of that. That does not apply when we have 2 nonmetals. So we have something like C3F4. Okay, this is a nonmetal, and this is also a nonmetal. So I know I'd need to use prefixes. So I'd use a prefix to describe how many carbons I have, not a flip-flop of how many fluorines. We just go, how many of the carbons do I have? I have 3 carbons. The prefix for that is tri. So this would be tricarbon. Then we're going to take the base name of the second element and we're going to IDE it, like we did with the ionic stuff. So instead of saying fluorine, we would say fluoride. And I have to put a prefix in the front that tells me how many fluorines I have. In this case, I have 4. So the prefix for 4 is tetra. Tetrafluoride. Tricarbon tetrafluoride. 3 of these and 4 of these. And that's it for naming the moleculars. It's that simple. Okay, it's so much easier than the metals and the nonmetals. Let's look at the list of prefixes. So mono is 1, di is 2, tri is 3, tetra is 4, penta, like a pentagram, is 5, hexa is 6, hepta 7, octa 8, nona 9, and deca 10. So you'll want to know 1 through 10 for your prefixes, or be able to access them. There are a couple exceptions. Well, there's really only one exception for when we drop a prefix. And that is if you happen to have 1 on the first element, you can drop the mono on the first one. Not if you have 2 of the first one on the first one, or 3 on the first one, or 4 on the first one, that you cannot drop. But if you have 1 on the first one, you can drop it. So let's look at this thing right here, CO. Based off of our system, we would call this monocarbon monoxide. Now, I've never heard anybody call it monocarbon monoxide. Why? Because we drop the mono on the first guy, but we keep the mono on the second guy. So this becomes carbon monoxide. If I, instead of having CO, I had C2O, some made up compound, there are 2 carbons, so I don't get to drop the di. So I would have to call this thing dicarbon monoxide. Okay, again, the only time we ditch a prefix is if there's one on the first, one on the second stays, any other number on the first stays. So, I mean, that's it for those. Those ones are so easy compared to all that work we have to do for metals and non-metals. We're still going to do some practice on it though. So let's, we'll go both directions. So I'll give you some formulas and I want you to write the name with the correct prefix, and then I'll give you the names with prefixes and you write the formula. Shoot, I don't have a periodic chart. N3F7, Si2, Cl2, S5, Cl8, P4, Er. And then I'll give you some names. Pentacarbon, dioxide, hexa, sulfur, non-fluoride, phosphorus, trinitride, sulfur monoxide. Okay. Give me the name here. Name it. Formula it. Don't flip flop. Don't do any of that. Need another minute on these. Okay, so when you come across something that is molecular or it's two nonmetals like this, leave charge neutrality in the past. Leave flip-flopping in the past. We are going to look at whatever the number is, and that will become the prefix for its respective element. So I have 3 nitrogens here. That becomes trinitrogen. And then we have 7 fluorines. So that's heptafluoride. Okay, so trinitrogen heptafluoride. It makes us sound so smart, doesn't it? So next one here, there's 2 and 2. We don't reduce in molecular. In ionic, I know we would like slice that down to do a 1-in-1 relationship. We're not going to do that here. So we do need to apply the 2 for each one. So this becomes disilicon. And I know silicon is a metalloid, but we can treat it as a nonmetal. So disilicon, difluoride. And remember that we are IDEing that second guy. This here, 5 is pentasulfur. 8 is octachloride. Down here, we've got 4 phosphorus, so tetra phosphorus. And then I have 1 bromine, but I do need to specify that I have 1 because that 1 is on the second one. So I'm going to have to call this thing mono bromide. Okay, we don't ditch mono if it happens to fall on the second one. Just remember your carbon monoxide. No mono on the first, mono on the second. For writing the formula, we look at these prefixes and that becomes the subscript for whatever element they're talking about. So pentacarbon is 5 carbons. Dioxide is 2 oxygens. And you're done. Hexa, 6 sulfurs. Nana, 9 fluorines. You can see that these could technically be reduced down, right? If we were to divide each thing by 3, but we don't reduce with molecular. So write a note somewhere that says no reduction with molecular. You do reduce if it's ionic, but not if it's molecular. Phosphorus trinitride. Okay, there's no prefix on this thing. That's because we have just 1 of them. And we don't have to say monophosphorus. So just phosphorus, and then trinitride is talking about 3 nitrogens. Sulfur monoxide. Again, no prefix here, so we assume that there's 1. And then monoxide is one oxygen, SO. Isn't that refreshingly easy compared to the flip-flop of metal and non-metal? No? Yes. I always find it nice to do that one, though. It seems like so quick after the ionic. What I don't want you guys to do, though, is to pull any of these rules back into the ionic stuff. All right. So when we see something like this, Al2O3, this is ionic type 1. Okay. So this is simply aluminum oxide. I can't tell you how many times I see students go, well, there's 2 of them. So this is dialuminum trioxide. This is oxide. This is totally incorrect, okay? Why? Because we do not use prefixes in an ionic compound. Prefixes are reserved for nonmetals. So if there is a metal, that first thing you bump into when you're looking at your formula is a metal, we do not prefix it. Save the prefixes for 2 nonmetals. So it's like when they all get kind of jumbled together, and we've got molecular and ionic and type 2s and polyatomic ions, that's where it gets a little tricky. So the best thing you can do is just practice, 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 because understanding the rules and the concepts will get you to that like 80, 85%. If you want to take it to like 100%, it's really in the details. So it's repetition, mastery, so that you remember all those little details about all the different polyatomics and everything like that. There is one other thing that we need to work on naming, and that is acids. Oh, there is something to denote as far as like vowels are concerned. So when the prefix ends with a vowel and the base name starts with a vowel, the first vowel is sometimes dropped, but sometimes it's not dropped. So monoxide is not monooxide, it's MON, and we drop one of the O's. But diiodide, we keep the double vowel, and triiodide, you keep two I's next to each other. It's very weird. I will not test you guys specifically on that. I won't give you one that says triiodide with one I and one that says triiodide with two I's. It will be clearer than that. Okay, so if we are going to name an acid, we first have to classify that it is in fact an acid. And we're going to spend a whole chapter at the end of the semester talking about acids and bases, but for right now, you're going to classify anything as an acid that if we were to put it in water or dissolve it in water, it would break apart into ions, and one of those ions would be hydrogen. So HCl, when I drop that into water, we're going to get H plus and Cl minus. Another way you can identify an acid, it's going to have H written in the front. That first thing you knock into is going to have an H. You're going to say, okay, that's an acid. There are two ways that we can classify an acid. We can say that it's either a binary acid, and a binary acid, bi meaning two, like a binary star system, that contains hydrogen with just some sort of nonmetal, fluorine, chlorine, bromine, one other thing. An oxyacid is when you have hydrogen, and it'll still be written first, the hydrogen, and it'll be combined with a nonmetal and oxygen. It's contained with a polyatomic ion. Okay, so it'll be like hydrogen mixed with sulfate or nitrate or something like that. So the way that we name these, first decide, is it binary or is it an oxyacid? So a binary acid would be, an example would be HBr or HCl. You could even have something like H2S. Anytime you just have two different things. An oxyacid would be HNO3, okay? H2SO4. Anytime that we've got these polyatomics in there, we call those oxyacids. And how we name those are different. So you want to be able to identify them. We'll start with the simpler of the two. So a binary acid, this is how you name it. You write the word hydro. That kind of takes the place of the hydrogen. You take the base name of the nonmetal and you, instead of iding it, you ick it. Okay, so this thing right here, HCl, I'm going to write, and then you end it with the word acid. So I'm going to say hydro. I take the base name of the nonmetal. In this case, the nonmetal is chlorine. So chlor, and I IC it, chloric. And then I add the word acid. You guys heard of hydrochloric acid? That's where the name is coming from. This thing right here, HBr, okay? It's a binary made of two things. So we're going to call this hydrobromic. We ick it, and then we add the word acid, hydrobromic acid. Okay. That works for all the binary acids, except there is one that you don't abbreviate, and that is this guy right here, H2S. We don't call this hydrosulfic acid, we call it hydrosulfuric acid. So we use the whole word sulfur. Just how it is. If we have a oxyacid, so we are combining our thing with a polyatomic ion, like this here, HNO3, that is nitrate. H2SO3 is sulfite, and H2SO4 is contains a sulfite ion, or a sulfate ion. So anytime we have one of these 8 or 8 ions, we go with it being an oxyacid. When naming an oxyacid, you want to look at the ending of the polyatomic ion. If the ending of the polyatomic ion is ite, ite changes to us, and you add the word acid. There is no hydro. Okay, we don't say hydro base name us acid. We just call it us acid. So let's go back to that HNO2. This thing right here is called nitrite. Okay, if we end in ITE, we become us. So I'm going to call this thing nitrous acid. Nitrous acid. What if instead of HNO2, I had HNO3? That polyatomic ion is not nitrite, it's nitrate. What happens to eights? Eights become ick. Like you ate something icky. Okay, 8 becomes ick. So this would be nitric acid. Nitrous acid, nitric acid. And we have a comment in here. Yes, so to clarify, Betsy, oxyacids do not list the word hydro. We don't call this nitrous acid, we just call it nitrous acid. Eights become ick, ites become us. The next page here shows us some of the varying acids we have out there. Take a look here and here. So this is the sulfate ion. This is the sulfite ion. Eights become ick, ites become us. We use the whole word sulfur for this though. This will be sulfuric acid and this will become sulfurous acid. H2CO3, this is the carbonate ion. Eights become ick. This is carbonic acid. Again, 8 becomes ick, acetic acid. You probably heard of acetic acid. It's in like all sorts of products that we use, a lot of food products, help with preservation. And then that is it for naming. So this is really helpful, actually. This is sort of like a giant flow chart to show us all of the different naming in one place. So pretty much everything we've gone over. So the first thing you want to do when naming anything, if you're looking at this chart, is to decide, is what you're looking at ionic? Is it molecular? Or is it an acid? Let's say you've got, we write this thing here. Do a couple examples. Na2SO4. So I'm looking at this thing. I want to go, is this ionic? Is it molecular? Or is it an acid? This thing is ionic. Why? It's a metal combined with some sort of non-metal. So I know I need to stay in this part of my flow chart. I'm ionic. And the next step is to determine, am I type 1? Do I predict, or do I form one predictable charge, or do I form more than one type of ion? And sodium is in column 1, so it forms a predictable charge. So we're going to go here. Okay. From there, we drop down. It doesn't give us the exact detail about a polyatomic ion, but just remember, if you have a polyatomic ion with a metal, you just say the name of the polyatomic ion. So I'm going to say the name of the metal with the polyatomic ion. This would be sodium sulfate. There are no dyes, there are no tetras, because we've classified it as ionic. Now, if I gave you something like this, S2O4, you'd look at this and say, okay, that's a nonmetal and that's a nonmetal. I need to be in this part of my chart. So I drop down, and what does it tell me? It says, hey, name the first element, sulfur, and give it a prefix, disulfur. Name the second thing, but ide it, and give it a prefix, disulfur tetraoxide. Okay, or this thing here, diphosphorus pentaoxide. if last case scenario, you know, I gave you something like this, H2 CO3, you're going to want to go, is this ionic? No. Is it molecular? No. This thing is an acid, okay, because we see that hydrogen written first. So now I need to say, is it binary or is it an oxyacid? Anytime it's got one of those polyatomic ions, we go over to the oxyacid section. This thing here is called carbonate, so it ends in ATE. So I know I need to go with the base name of the oxyanion, carbonate. We'll go with carbon, and we ick it, carbonic acid. Carbonic acid. You guys seeing how to work this chart? It's a really useful chart to have. You start broad and then you go down and get more detailed. So I would recommend having this when you're working on like your lab. It's going to be pretty useful. So any questions on naming thus far? And that's the end of the chapter. I'm not going to leave yet though. I'll hang around and let you guys have some time to work on your lab. And if there's any of the ones that you want to work on from your lab manual, like number 16 is, you know, driving me crazy or something, I will go ahead and go over it. If you are done, then you can go. Just make sure your lab is completed before you turn it in, or before it's turned in on Sunday. So I will leave this chart up for right now. If you need a minute, go grab your lab manual. If you're done for today, I will see you next week. And then feel free to throw your mute off or throw in the chat things that you want help with. I'll just be here. No problem, Juan. Have a good weekend.
I actually have a couple of questions, but they're
Cynthia,
from the
I hear
worksheets.
you. You're trying to chat with me.
Yes. Can you hear me?
It might be on my end. Let me turn my volume up. Hold on. I think it's me. Right now.
Can you hear me?
Yeah, now I can hear
Okay. I wasn't sure because I keep having connection problems. Last week I got kicked off like 3 times, you know,
No,
so I don't know.
that was totally me. I had the volume all the way down. So what's that?
Well, it's not exactly the lab. It's some of those extra worksheets
Mhm.
that I have a couple questions about, just in
Okay.
case there were issues on the lab. Like, for example, I noticed, let's see, I don't even know how to say this one. Is it yttrium?
Mm-hmm. Why?
Yeah, so it
Mhm.
has YClO3. So
Okay.
I put hypochlorite, but it looks like
So
I'm not supposed to put a 3 there. So why wouldn't I put a 3?
they're not wanting a 3. I would want you to have a 3 on it.
Okay, that's what I wondered about. And the
Yeah.
other one was a cadmium. Does cadmium usually have it or no?
So cadmium has a predictable charge of 3.
Okay.
Scandium also has a predictable charge, but I don't want to give you all the ones that are predictable because you don't have to memorize. I don't want you to really memorize or fill your brain with too many of those. So really, as long as you go with aluminum, zinc, and silver as having predictable charges, I will accept systematically that the other ones are varying charges and take the additional Roman numeral.
Okay.
Okay. But yeah, cadmium does have a predictable charge. So it's 3+.
Trying to see if there were any other ones, but I think, yeah, because the couple of those threw me off, and I was like, why did they not have Roman numerals? I think they're supposed
Yeah,
to.
well, those are very educated questions. Definitely good questions.
But for anybody that hasn't done those, in case everybody else can hear me, they will definitely help you breeze through the lab and through the homework.
Yeah.
If
And I will, if you want to, if anyone wants to as well, if you've gotten the lab done or before you turn the lab in, if you want to email it to me, I will take a look at it and I'll let you know which ones you got right and or which ones you got wrong. So you can go back and fix them if you want to before turning them in, just in case.
Yeah, because those helped me so much. Like I felt
Mhm.
like when I started doing the lab, I was just like breeze through it. And even the homework, even though I kept, I did some stupid stuff. Like for some reason I got hung up on, what was it? The try and what's the fourth one? The
Petra.
Petra. And for some reason in my head, I knew the difference, but I just kept doing the opposite one. It made me so mad. So
Yeah. Try like a tricycle, 3 wheels. A tetrahedral has 4 corners.
yeah, and I know that it just, I kept, it was one of those, like, I think one time I put in calcium instead of chlorine, and I know the difference, but it was calcium had been used in the activity before.
Mhm. And
You know,
that's why I tell everyone with this, specifically with this section, because it's so detail oriented, that like if you miss a charge or you do something silly like that, you'll miss the answer, even though you know the system. And so it's like as much as you can practice with these, the better you're going to be at it, the less chance you're going to make silly mistakes like that. So,
Okay. Well, thank you.
all right, Cynthia. If you want to at some point too, feel free to email me your lab
Okay.
and I can take a look at it.
Okay, great. Sounds good.
Okay. So if you've got your lab out, if you have any questions on the ones that you are looking at, let me know. Okay, Grayson. So you're unsure on a reference sheet for like polyatomic ions? How to locate the information to look at. So like, do you have the charges written on your periodic chart?
So that's really all I have. Like I wrote down everything that you told me to write down, and I've been
Okay.
taking notes during the lecture, but
So you'll want, so some things that you'll want to have is like a polyatomic ion sheet. Hold on one sec, let me clear this out. Can you see my screen?
mhm.
Okay. So if you go into like a Google search and you just type in polyatomic ions, you're gonna come, it's gonna come up with a bunch of like options for you. Just pick whichever one kind of works for you. But you know, like if we click on this one, here's like most of the polyatomic ions that you're gonna come into contact with. Okay, so sulfate, carbonate, that one. Let's see this one. Yeah, this is a good one too. So it has a bunch of the polyatomic ions. That's
So
probably
just
one thing you want to have.
Type in the common polyatomic ion chart. And use
Yeah.
it.
Yeah. It's also in your textbook. So you can go to this chapter in your text and they have a polyatomic ion sheet as well. I think here, if we go to the slides and we go where are you? Back up here, there's quite a few of the polyatomic ions with their respective formulas. That's a good thing to have. And then, you know, you want, I mean, you've already got the charges. Are you good with like the abbreviations? Like fluorine becomes fluoride. So this is just what we, like when we have a metal and a non-metal, like sodium with, for instance, sodium and chlorine, we don't call that thing sodium chlorine, we call it sodium chloride. So these are just the base names that we use. We just use the first syllable of each one.
Okay. I think for me is like I got a lot of just fear because it's so much information and I just don't know where to find it all. And
I would
know
say
can-
like this really is everything sort of summed up. So if you can, you know, if you take a formula, whatever it happens to be, and you start naming it, this is where you want to start. You want to decide, is it ionic, is it molecular, or is it an acid? If you decide, for instance, it's ionic, follow the flow chart down so you can use the steps, right? If it's predictable charge, it's a metal with the ided non-metal. If it's an unpredictable charge, you have to add the Roman numeral. If it's molecular, you've got your prefixes, and then acids has their own set of rules. So I think this is really helpful for that. But part of it is just practicing. You just gotta.
I think that's it. I just haven't.
It like, because you're not. I mean, you can understand it in theory, but it's not like.
Yeah.
You know, studying for a history test. At some point, you've just got to start like doing them and then checking and seeing if they're right. So what you can do is you can always work on the lab, and if you want to get that to me at some point before you turn it in, that's a good way to practice. And I will let you know which ones are right and wrong. There's also the Mastering Chemistry will be a lot of help with this. You just have to do it.
Yes, ma'am. Well, that's I'll be honest with you, Miss Henderson. That's like my biggest fear is like when I struggle with understanding this, I do go to the tutoring center online and they help me and they're great.
They're awesome.
But I don't want them to help me do it all and then I can't do it when I'm by myself. And that's like my biggest fear because
totally.
I just feel a little lost right now.
That's understandable. So what you could do if you want to is work with the tutoring lab on the homework. And then when you get the lab, do the lab on your own. So that you can use the lab as like a practice to see if you've got the skills.
So get help with the homework to understand it more and then do this lab on a separate sheet of paper and get the tutor to check my answers and then turn in the right one.
Or I can check your answers too. If you get the lab done, I'll check it for you before we grade it. So if you get it done on like Friday or something, just email it to me and I'll look over it and see how you're doing.
Okay.
And then there are some worksheets that have the answers. So here, come along. Let's look at our Moodle page.
Can I butt in for a second? Just a second.
Yeah.
On one of those worksheets too, because I know you were talking about the polyatomic ion chart. I think it's the first extra worksheet. It's got like a little chart.
It's got them.
It's got a lot of them. I mean, it's that one. Like there's the answers. And then I think it's after that. There's like a little table.
Yeah, so all these worksheets have the answers to them. So that's a good way to practice. Oh yeah, here we go. So here's the polyatomic ions. Well, some of them.
It doesn't have all of them, but
it has some of them.
It's been helping me a lot. So
yeah. So, you know, these worksheets are useful. Like, it's a bit.
Is this almost like pure, like, is this to try to develop like pure memorization of like particularly common?
It's not. Oh, you mean for the polyatomic ions?
Yeah.
The polyatomic ions are sort of memorization, yeah, but because you guys are on the online format, you'll get to have, you can, if you have this chart, you can use it during an exam.
Okay.
Okay, in person, you would have to have these memorized,
Yeah.
and there's no real fancy way to like
Yeah.
read it off the periodic chart. You just have to memorize that sulfate is SO4 with a 2- charge. That's memorization. But the naming part shouldn't be memorization. You shouldn't like memorize what this name is because there's just way too many compounds. What you need to know is the system that then will help you name all these things. And you've got formulas that you can name, and then you've got names that you can transfer into formulas. And then you have all the answers. So you can go back and compare and see if you did it right or not.
And
And
then,
there's four worksheets here. That would be probably
Thank
pretty
you.
useful.
on the periodic table, like I know in column 1 you told us to put the 1+ charge. In column 2 I got the 2+ charge, and then I don't I don't have anything in the transitional elements. Is that because that's going to be the ones you're determining?
Mhm.
And then
Yeah, those
so
are going to
that-
be varying charges, except, well, aluminum put the 3+, zinc put the 2+, and silver put the 1+. Do you have
So
those?
it's not that entire column. It's just silver is the only one in that column.
Yes, silver is
zinc
the
is
only one in that column, and zinc is the only one in that, and its column. Okay,
And
so
then-
those we treat like main group elements. All the other transition metals, for the most part, have varying charges, so that's going to need the Roman numeral.
And then I don't have anything for column 3 or 4, and then I have 3 negative at column 5.
Yeah, yeah,
Is that how
that's
it's supposed
fine.
to be? Okay.
Yeah,
I thought
yeah,
that
I
I
mean-
missed some for some reason that
no, I mean, so like the silicon carbon column, they can take on 4 electrons or give up 4 electrons. They usually don't transfer electrons though, because they need to get rid of and or take on so many. So they usually just share electrons. So we don't really put anything in that column. But
Okay.
nitrogen and phosphorus, you do want that to have a 3-, the oxygen, sulfur 2-, and then the fluorine, chlorine, bromine, iodine, you want that to be 1-, and then nothing above the noble gases.
okay. I got all that. I just thought for some reason I thought that I had something missing in 3 or
Mm-mm.
4.
No, you won't see really metals getting mixed with like silicon and carbon very often. So
Okay. Thank you. Yeah, I think I just got to practice. I appreciate it.
I think you just, yeah, Grayson, I think you're overthinking the like logical component of it, and you've just got to get your hands dirty and practice.
Okay.
Yeah.
Thank you so much. I
All
appreciate
right.
it.
Mhm.
Have a good one.
Yeah, you too.
I have a question, if I may.
Yeah.
I am reading the very first question on the compounds, and the
Uh-huh.
way I've been writing